You can lie down now. Let your body sink into the bed and let your eyes rest. This is your time to settle in and let your mind drift in a gentle way. As the room becomes quiet, the story will move at a slow pace, steady and calm, almost like a soft breath you do not need to think about. One simple question begins everything. How do we know when a distant planet might support life? This question has guided years of study, long nights of watching stars, and careful work that demands patience and steady focus. It is the same question that eventually led scientists to a planet called Kepler 442B, far beyond anything the human eye can see. The story starts with a basic idea. For a long time, people wondered if stars other than the Sun had planets around them. This was only a guess at first, because our tools were not strong enough to see the tiny change a planet makes when it moves around a star. A star is bright, and a planet is small and dark, so the planet hides inside the light. As technology improved, scientists learned how to measure very small changes in starlight. This allowed them to search for worlds that had been invisible for all of human history. All of this effort led to the Kepler Space Telescope. Kepler was built to stare at one large patch of the sky and measure the brightness of many stars at the same time. It did not look for planets in a direct way. Instead, it looked for a drop in light. When a planet passes in front of its star, even by a small amount, the star becomes a little dimmer. Kepler was sensitive enough to see this small change. This method is called the transit method, and it allowed Kepler to find thousands of planet candidates by watching the same stars again and again. One of these stars was named Kepler 442. It is an orange star, cooler and smaller than the Sun. Stars like this are called K-type stars. They burn fuel slowly and live much longer than stars like ours. Their calm and steady light is one reason scientists look at them when they search for planets that might hold conditions for life. Kepler 442 sits far from Earth, more than 1,000 light-years away, in the direction of the constellation Lyra. Its light takes many centuries to reach us, yet it carries clues about the world that circles it. Kepler saw the light from Kepler 442 dim at regular times. Each dip happened after the same number of days, which meant something was moving around the star in a steady orbit. From the amount of dimming, scientists could estimate the size of the planet. From the repeating pattern, they could find the length of its year. These pieces of data, even though simple on their own, allowed researchers to calculate that the planet is about 1.5 times larger than Earth. They named the planet Kepler 442b. It became one of the most interesting findings because the numbers matched what scientists look for when they study habitability. The planet orbits in what is called the habitable zone of its star. This zone is the region where temperatures might allow liquid water to exist on a planet's surface if the planet has the right kind of air. For Kepler 442b, the star's lower brightness makes the habitable zone much closer than it is around a star like the Sun. The planet completes one orbit in about 112 days, which is the length of its year. The strength of the planet's gravity can be estimated from its size and probable mass. It seems strong enough to hold on to an atmosphere, though we cannot yet measure what the air might be made of. This is one of the biggest limits of our current tools. We can see the planet pass in front of its star, but we cannot see its surface, and we cannot capture the exact chemical fingerprint of its air with the data we have now. Even so, the basic facts place Kepler 442b among the most promising known worlds for possible habitability. The star itself adds to the interest. A K-type star gives off less harsh radiation than very young or very active stars. Its stable light creates a better chance for a planet to keep its air over long periods of time. A star that lives for tens of billions of years gives a planet a long window in which stable conditions might form. These ideas make Kepler 442b stand out each time scientists compare known exoplanets in the habitable zone. Even with all this progress, many questions remain. We do not yet know how fast the planet spins, or whether one side faces the star at all times. We do not know the details of its clouds or land, or if it even has oceans. But what we do know comes from careful measurements, built piece by piece, each one adding a small part to the larger picture of this distant world. Kepler 442b sits in a place where conditions could be right for life as we understand it, which is rare in our current catalogue of planets. As more telescopes and instruments grow stronger, they may provide new information about this world. Scientists hope to learn how thick its atmosphere is, how much light it reflects, and whether its air shows signs of water vapor or other important gases. Everything so far points to this planet being one of the most promising targets for habitability, even though the distance makes direct study slow and challenging. This is where the search now stands, steady and careful, moving forward with patience and quiet focus. Each new observation of Kepler 442b adds a small piece to the long and calm effort to understand planets beyond our own solar system. The planet remains a point of interest because it sits in the right place, around the right kind of star, with the right size and likely mass to hold a stable surface. These measured facts keep it among the top candidates when scientists talk about planets that might be able to support life. Kepler 442b draws interest not only because of its position, but also because of what its measurements suggest about its structure. A planet of its size is likely rocky, which means it may have a solid surface instead of a deep layer of gas. Scientists base this on statistical studies of planets with similar radii. When a world is much larger than twice Earth's size, it often contains thick layers of hydrogen and helium. Kepler 442b stays below that range, so the chance of it being a rocky planet is high. The planet's path around its star gives more clues. Its orbit is nearly circular, based on the steady timing of each dip in starlight recorded by Kepler. A circular orbit helps maintain steady temperatures because the planet does not swing too close to or too far from its star during its year. This stability matters when looking at habitability. Sharp temperature swings can make it harder for long-term surface conditions to remain steady. Kepler 442 itself also helps shape the possible environment. As a K-type star, it produces light that is softer than the light from hotter stars. It releases less ultraviolet radiation, which can strip away a planet's air if the star is too active. A calm star allows a planet to keep more of its atmosphere over time. Stars like Kepler 442 are known for stable energy output, which creates a more even supply of heat for planets in the right region around them. While the known facts create a promising picture, there are still many gaps. For example, we cannot yet measure the planet's atmosphere directly. To study a planet's air, scientists need to detect the tiny change in starlight that passes through the atmosphere during a transit. This technique requires high sensitivity. Kepler was not designed for this type of work. Newer telescopes, like the James Webb Space Telescope, are better suited. But the distance to Kepler 442b makes the signal very faint. Even without atmospheric data, scientists can estimate how well the planet might hold onto air. A world with a larger radius than Earth likely has stronger gravity. Strong gravity helps keep lighter gases from drifting into space. If the planet formed with water or other volatiles, it may have been able to keep them over long periods. This is important because water and stable gases help shape surface conditions that can support life as we know it. Another factor scientists consider is the planet's rotation. Kepler 442b orbits close enough to its star that it might be tidally affected. This means the same side could face the star all the time. We cannot confirm this with current tools, but it is a possibility. If the planet is tidally locked, one side would receive constant light while the other stays dark. Models show that with a thick atmosphere, heat can spread across the surface, reducing extreme temperature differences. Without a substantial atmosphere, the contrast would be strong, creating a hot side and a cold side. Understanding which case applies to Kepler 442 requires future study. The age of the system also shapes what scientists think about this world. A K-type star lives far longer than stars like the Sun. This long lifespan allows planets in the habitable zone to stay in that zone for billions of years. Long periods of stable conditions increase the chance for an atmosphere to remain intact. If the star is older and stable, the planet may have had enough time to develop steady surface environments, though we cannot observe them yet. Distance is one of the biggest limits on what we can learn. Kepler 442 lies more than 1,000 light-years away, which means any signal we receive is faint. The farther a planet is, the harder it is to measure details about its air, clouds, or surface. Even so, scientists continue to watch for any new data that might improve the picture. Each new telescope helps refine the numbers, even if only by small amounts. Because of its position in the habitable zone and its size, Kepler 442b appears often in discussions about promising planets. Many exoplanets have been found that are larger or smaller, or orbit stars that are too hot or too active. Some lie outside the habitable zone. Others probably have thick atmospheres of hydrogen that create surface pressure too high for liquid water. When researchers compare all known options, only a small group seems to meet basic conditions for habitability. Kepler 442b repeatedly stands out in this short list. The planet's year of about 112 days places it closer to its star than Earth is to the Sun. But because the star is cooler and less bright, the heat received by Kepler 442b falls within a range that may allow water to remain liquid. This balance between distance and stellar heat plays a major role in shaping the planet's potential environment. The numbers suggest that the surface, if rocky, may receive a steady amount of energy, though not as much as Earth. Kepler 442b has also gained attention in studies that look at the Earth Similarity Index. This index compares factors like size, density, and distance from the star to estimate how Earth-like a planet might be. Kepler 442b scores high on this scale. The score does not confirm habitability. It simply shows how closely the basic traits match those of Earth. These measurements help guide further study and direct new instruments toward the most likely candidates. The search now focuses on how to study planets so far away with better clarity. Scientists look at ways to improve radial velocity measurements, which can reveal a planet's mass. Mass leads to density, which tells us even more about the planet's structure. If new instruments can measure the slight pull Kepler 442B exerts on its star, researchers will gain a clearer picture of whether the planet is made of rock, metal, or lighter materials. Future missions may also allow more detailed study of its atmosphere, if enough light can be gathered during a transit. Detecting gases requires capturing the star's light as it passes through the thin layer around the planet. Each gas absorbs light at specific wavelengths. By measuring this, scientists can tell if important components like water vapor, carbon dioxide, or oxygen are present. This is difficult at great distances, but the method has already been used on closer planets. If applied successfully to Kepler 442b, it would offer a major step forward. For now, Kepler 442b remains a quiet signal inside a large field of stars. Its measured traits create a steady picture that holds interest, a rocky world of moderate size, receiving the right amount of light, orbiting a calm star that may support long-term stability. Its distance limits what we can see, yet the numbers point to conditions that match what researchers search for when they look for a world that could support life. Even with limited data, scientists gain more insight by comparing Kepler 442b to other planets found around similar stars. When they study groups of exoplanets that share size and orbit traits, patterns appear. These patterns help estimate how common rocky planets are in the habitable zones of K-type stars. Kepler 442b fits into one of the most promising patterns, a world of moderate size in an orbit where steady light is possible. By placing it in this wider context, researchers can see how typical or rare such planets might be. Looking at the star itself adds more detail. Kepler 442 shows signs of low activity, which means it does not produce strong bursts that could damage a planet's air. Telescopes track small changes in brightness to look for star spots and flares. The records show a calm star with gentle changes over time. This behavior is helpful because it suggests that the planet has not been exposed to extreme radiation that would strip a thin atmosphere. A steady star also creates predictable conditions that help models estimate the planet's energy balance. Energy balance is important because it shapes surface temperature. A planet absorbs light from its star and releases heat back into space. The balance between these two processes decides whether a world is warm, cold, or somewhere between. If Kepler 442b has clouds, they could reflect some light. If it has a thick atmosphere, it could trap heat. Without direct measurements, scientists can only run models using different possibilities. But many of these models show a range of temperatures that stay within the zone where liquid water might exist. Distance also affects the kind of light the planet receives. K-type stars shine with more orange and red light than the Sun. This light carries less energy per photon than blue or ultraviolet light. On a planet in the habitable zone of such a star, the surface would receive steady warmth without sharp spikes of harsh radiation. This may help any atmosphere remain stable. It may also shape how energy spreads across the planet. Some models show that redder light can warm surfaces differently than sunlight does on Earth, though the exact patterns depend on surface materials and the presence of air. Over many years of study, researchers have built a clear picture of why K-type stars are strong. candidates when searching for possible life-bearing worlds. These stars live far longer than our Sun and fade slowly. A long lifespan reduces sudden changes that could destabilize a planet's climate. In systems where the star remains steady for billions of years, the worlds around it have more time to settle into long-term conditions. This idea strengthens interest in Kepler 442b because it orbits a star that may offer such long stability. Another point scientists consider is how planets form around stars like Kepler 442. Disk studies around young K-type stars show that they often have enough material to form rocky planets of many sizes. The position of the habitable zone moves as the star grows older. When a star is young, it is often brighter. Over time, it becomes dimmer and more stable. If Kepler 442b formed early and moved slightly inward due to interactions with other forming planets, it may have settled into the habitable zone once the star reached a steady phase. Though this is only a general formation pattern, it helps explain how planets end up in certain orbits. Researchers also study how the world's mass influences its inner structure. A planet larger than Earth can maintain a warmer interior for a longer time. A warm interior may create volcanic activity, which can release gases into the air. On Earth, volcanic gases played a major role in shaping the early atmosphere. If Kepler 442b has a similar process, it could have kept a supply of gases over long periods. A thicker atmosphere would help spread heat between different regions, especially if the planet rotates slowly or is tidally affected. Even with so many unknowns, each new mission adds small pieces that strengthen the picture. The Gaia spacecraft, for example, helps refine the distances to stars across the galaxy. When a star's distance is measured more precisely, its brightness can be calculated with greater accuracy. This, in turn, improves estimates of how much light reaches any planet around it. As distance data become more accurate, the models for Kepler 442b's temperature range become sharper. This helps scientists rule out extreme values and focus on the most likely range. Large ground-based telescopes also help. Instruments that measure slight stellar motions can confirm the presence of planets and help refine their masses. These measurements rely on complex tools, but the effect they detect is simple. A star moves slightly as its planet orbits, pulled by gravity. The movement is tiny but measurable. If future observations detect this motion for Kepler 442, scientists will know more about Kepler 442b's density. Density reveals whether the planet is made mostly of rock, heavy metals, or lighter materials. All these efforts share one goal: to understand what conditions are possible on a world we cannot yet see directly. Kepler 442b remains only a dim signal in a distant star field, but its known numbers point toward a promising profile. A calm star, Mars' good orbit, and a likely rocky body create a combination that fits what researchers look for when searching for a planet that might support stable surface environments. These traits do not guarantee habitability, but they help place Kepler 442b among the most studied candidates. Kepler 442b's distance from its star also shapes how much radiation reaches its upper atmosphere, if the planet has one. High-energy radiation can break apart molecules, causing gases to escape into space. Because Kepler 442 is calmer than many other stars, the rate of this loss would be slower. A slow rate allows an atmosphere to stay thick for long periods. Even without direct measurements, the known stability of the star helps researchers estimate how well a planet in that orbit could retain its air. models also consider the planet's possible surface gravity. A world with a radius about 1.5 times Earth's size likely has stronger gravity at the surface. Strong gravity pulls gases inward more firmly. On Earth, this helps keep air close to the ground, but on a larger planet, the effect would be even stronger. If Kepler 442B formed with water vapor, carbon dioxide, nitrogen, or other simple gases, this pull might have helped keep them from drifting away over long stretches of time. Surface gravity affects more than the atmosphere. It can shape the height of mountains, the depth of valleys, and the flow of liquid water, if water exists there. On high-gravity planets, geological features tend to be shorter because rock cannot support tall structures as easily. This detail may seem small, but it helps scientists imagine what a rocky world of this scale might look like. Even without images, the physical rules that shape landscapes allow them to picture broad patterns. The star's age adds more clues. Measurements suggest that Kepler 442 is older than the Sun. An older star has had more time to clear away debris left over from the early stages of its system. A cleaner system reduces impacts from large objects. On Earth, heavy impacts in its early history changed the surface many times. A planet around an older star might have experienced fewer recent impacts, giving it a calmer, more settled surface. This could help maintain long-term stability if the planet already had an atmosphere or surface water. Kepler 442b's orbit places it at a distance where the star's light is steady enough that large seasonal changes are unlikely. Earth experiences seasons because its axis is tilted. Whether Kepler 442b has a tilt is unknown, but even if it does, the amount of light from a K-type star spreads over time in a smooth pattern. This reduces sharp climate swings. A stable flow of energy is one of the strongest indicators of a world that might maintain long-term surface conditions. The study of exoplanets often moves forward by refining star measurements, and Kepler 442 is no exception. When scientists better understand the star, they automatically improve everything they know about the planet. A slightly different value for the star's radius changes the estimate for the planet's size. A more precise reading of brightness changes the estimated amount of light that reaches the world. These adjustments may seem small, but they help narrow the possible environment of the planet. Kepler 442b also helps scientists test ideas about how common Earth-sized worlds are in the galaxy. Each planet added to the data set makes the model stronger. When many worlds show up around K-type stars, it suggests that these stars often form planets with solid surfaces. If rocky planets commonly appear in the habitable zones of such stars, the galaxy might contain many more places with stable conditions. Kepler 442b acts as one of the key examples when researchers estimate these numbers. Part of what makes this planet interesting is how little it deviates from the expected pattern of a habitable zone rocky world. It is not too large, not too close to its star, and not too far away. Its star is not unusually active or dim. Many planets found by the Kepler mission show extreme traits. Some orbit so close that their surfaces may be molten. Others orbit so far that they may be frozen solid. Kepler 442b sits in a middle zone that is rare but important. Even with its promising traits, scientists remain careful not to assume too much. A planet can fit every basic requirement for surface habitability and still be uninhabitable for reasons we cannot detect yet. A world could lack a magnetic field, which would expose its surface to stellar wind. It could also be dry if water never collected there during formation. These details matter, but they remain out of reach for now. Still, the known data keep researchers interested because they meet the first level of conditions needed for a world to support life. The planet's distance from us creates a natural limit on current methods. Telescopes cannot yet take detailed images of such distant planets. They can only capture the tiny changes in starlight as the planet moves in front of the star. This means that much of what we know comes from indirect signals. Even so, these signals are consistent and reliable. Each transit gives another measurement of size and orbit. Over many years, these repeated measurements help refine the picture. Scientists also use computer models to explore how different atmospheres would react to the light from a K-type star. A dense atmosphere rich in carbon dioxide might trap enough heat to warm the surface. A thinner atmosphere with clouds might reflect some light and keep temperatures moderate. A water-rich atmosphere could create strong circulation patterns that spread heat evenly across the planet. These models do not tell us what Kepler 442 actually has, but they show what is possible under different conditions. A question that comes up often is whether Kepler 442b might have a magnetic field. A planet with a molten core can generate a magnetic field through rotation and internal movement of metal. A strong field protects the surface from charged particles that can strip away air. Without a direct measurement, the presence of a magnetic field remains unknown. But planets of similar size and expected composition often have enough internal heat to maintain one for long periods. Understanding magnetic fields also connects to understanding the star. A calmer star sends out fewer bursts of charged particles. This means that even if Kepler 442b has a weaker magnetic field, the strain on its atmosphere may still be manageable. The combination of a gentle star and a planet with strong gravity may help preserve air, even if the magnetic protection is modest. With each detail, the planet becomes easier to place within the broader map of known worlds. Scientists build layers of understanding by looking at its orbit, star type, size, likely composition, and energy balance. None of these pieces alone tells the full story, but when placed together, they create a steady picture of a world that fits many criteria for habitability. Kepler 442b stands as an example of how much can be learned even from faint signals across great distances. As the view widens across the planetary disk, the details of Kepler 442b's surface remain hidden beneath layers of uncertainty. Yet each clue from indirect measurements brings a clearer sense of what may lie there. The planet's gravity, for example, would feel stronger than what humans know on Earth. And that simple fact shapes the kind of landscapes that could exist. Steeper slopes might be rare, because stronger gravity tends to pull loose material down more quickly. Mountains might rise, but not as sharply. Valleys could stretch across long distances with gentle curves, shaped by slow forces acting over millions of years. These ideas come from basic physical rules that apply to any rocky world of similar mass, and they help scientists picture how pressure and weight interact on such a surface. Light from the host star also plays a major role in shaping the planet's environment. An orange-red star emits more of its energy at longer wavelengths, and that shifts the kind of light that would reach the ground. If clouds formed, their tops might glow with warm colors, instead of the bright white seen on Earth. Sunlight at the surface could feel softer, with a calm tone that spreads evenly rather than shining with sharp contrast. Instruments on telescopes cannot confirm these details yet, but the physics of stellar output allows researchers to infer a general view. The planet's rotation rate, still unknown, adds another layer of curiosity. If Kepler 442B rotates at a pace similar to Earth, it would create a pattern of day and night that guides wind, rainfall, and temperature variation. If it rotates slowly, the side facing the star could warm more than the far side, shaping strong global currents. Because the star is not extremely close, a locked rotation pattern is less likely, but it cannot be ruled out. Scientists analyze the star's magnetic activity and tidal forces to estimate how the planet might move, using models that compare many possible scenarios. These models help identify what conditions support stable air pressure. A planet of this size can hold a broad range of atmospheres, from thin to dense. A thicker atmosphere would help even out temperatures across the surface by trapping and moving heat. A thinner one would leave stronger temperature swings, but would still allow liquid water if the overall energy input from the star remains within the right limits. The broad window of possibility is part of what makes Kepler 442b notable. Several combinations of pressure, temperature, and composition remain consistent with a stable, temperate surface. Spectroscopy remains the key to reducing those unknowns. When starlight passes through a planet's atmosphere, gases absorb small parts of the light. The patterns of these tiny changes reveal which molecules are present. Earlier, telescopes could not measure such faint signatures, but new generations of instruments are approaching the precision required. Scientists expect that future observations may detect signs of water vapor, carbon dioxide, or other simple gases. Even a single confirmed molecule would narrow the possible atmospheric structures and help refine expectations about the climate. Water, in any form, remains the central focus of these studies. A stable supply could shape rivers, lakes, or oceans, and even clouds would signal active cycles that transfer energy across the planet. The presence of water does not guarantee habitability, but it increases the chances of a steady climate. Without direct observation, researchers rely on energy balance models that calculate how much of the incoming light is reflected, how much is absorbed, and how heat is released back into space. If the numbers fall within a specific range, the surface could support liquid water over long periods. Over time, more precise star measurements also help build confidence. Knowing the star's age allows scientists to estimate how its brightness has changed. Younger stars tend to be more active, sending out strong bursts of radiation. Older ones become quieter. Kepler 442 appears to be mature and stable, which suggests that the planet has likely experienced consistent energy levels for billions of years. Long-term stability matters, as it gives any potential environment time to settle into steady patterns rather than constant upheaval. As each clue fits into place, the picture grows richer, yet remains grounded in data. The planet stands as one of the more promising worlds found so far, not because of a single trait, but because many factors align in a balanced way. Its size supports a long-lasting core. Its orbit keeps it within a region where temperatures can support liquid water. Its star burns calmly, and the indirect signals gathered from distant instruments continue to match the conditions that tend to create gentle, moderate climates on rocky worlds. All of these insights guide the narrative toward a deeper understanding of how distant planets can resemble Earth in broad structure while remaining unique in every detail. The study of Kepler 442 becomes a slow and steady effort to connect physics, observation, and modeling into a clear view of a faraway world, one that may hold the quiet stability scientists hope to find. As researchers study more data about Kepler 442b, the role of its star becomes even clearer. An orange dwarf gives off less harsh radiation than hotter stars, and that difference shapes every process on the planet. The outer layers of the star move slowly, giving it a steady brightness that does not swing in extreme ways. This steadiness allows a planet in the right orbit to stay within a temperature range that changes only with natural patterns of seasons or rotation. For a world that may host liquid water, such consistency becomes one of the strongest signs of long-term stability. The energy the star provides sets the pace for weather cycles that could form if the planet holds an atmosphere. Warmer regions would lift air upward, cooler areas would draw it down, and gentle loops could form across the surface. The exact shape of these loops depends on rotation speed, land distribution, and atmospheric thickness, none of which are known yet. Still, climate models can test a wide range of arrangements, and many of them show that the planet could avoid extreme heat at its closest point to the star and avoid severe cold at its farthest. This helps explain why Kepler 442b is often placed high on lists of potentially temperate planets. The planet's mass also helps it retain lighter molecules that might escape from smaller worlds. A strong gravitational pull keeps gases from drifting away into space, especially over billions of years. This matters because stable air needs time to reach a balance between surface processes and sunlight. If gases escape too quickly, the climate swings wildly. If they build up too much, it creates a runaway greenhouse effect. A planet with the size of Kepler 442b can hold the kind of atmosphere that stays near equilibrium, neither thinning nor thickening too fast. Geologists use this information to think about internal forces. A planet with this much mass likely has a warm interior produced by leftover heat from formation and slow radioactive decay. Heat rising from deep layers can move through solid rock in patterns that form plates or large blocks. On a world this size, the crust might be thicker, which changes how often surface changes occur. A thick crust cools slowly, suggesting that large regions may remain stable for long periods. If volcanic activity exists, it might release gases that help build or maintain an atmosphere. Even if direct evidence cannot be seen, these ideas follow from well-studied planetary physics. The star's metallicity, the measure of heavy elements in its composition, adds more detail. Kepler 442's metallicity supports the idea that planets made of rock can form easily in its system. Heavy elements fuse in older generations of stars and spread across space when those stars die, seeding new systems with the building blocks needed for solid planets. Since Kepler 442 is neither too young nor lacking in these elements, the system likely formed with enough material to create planets with dense cores and thick mantles. Researchers consider how often the star emits flares. Some stars with lower temperature can show strong bursts of charged particles. These bursts can damage or strip atmospheres if they happen too often. Kepler 442, however, shows mild behavior. It does not produce constant violent outbursts. making it easier for any possible atmosphere on the planet to remain in place. Even moderate flares can shape upper atmospheric chemistry, but a stable star reduces the chance of severe long-term change. As instruments become more refined, scientists can measure the exact motion of the star over time, revealing subtle details about the planet's pull. These measurements help narrow down the shape of the planet's orbit. A stable, nearly circular path keeps the climate from shifting in extreme cycles. Early data suggests that Kepler 442 follows such an orbit, though more observations are needed to confirm this clearly. If the orbit is indeed close to circular, the planet spends its entire journey around the star, in a region where conditions can remain mild. The faint signals gathered from the star during transits also provide hints about the planet's overall reflectivity. A world with bright clouds reflects more light. One with thick forests or dark oceans would reflect less. While no one can see the surface yet, the range of possible reflectivity values can show whether the energy balance leans toward warmer or cooler surface temperatures. Many models show a balance that could support water remaining liquid if pressure allows it. Each discovery, though small on its own, fits into a steady chain of clues. None of these clues confirm habitability outright, yet together they outline a world that behaves like other temperate planets we know. The combination of mass, orbit, stellar output, and energy balance creates an environment where complex cycles might develop, even if the exact details remain hidden behind distance. Scientific teams continue to refine the data they have, aware that each improvement in sensitivity adds a new layer of clarity. Kepler 442B stands as a reminder that planets far from Earth can share familiar conditions in surprising ways, shaped by simple physical rules that apply everywhere in the universe. With every refined measurement, the picture becomes less abstract and more grounded in the quiet, steady mechanics of starlight, gravity, and time. The slow work of studying Kepler 442b continues through small measurements that build on one another. As telescopes improve, tiny changes in starlight during each transit show patterns that were once too faint to detect. These patterns reveal how the planet moves across the star's disk, which helps refine its size and density. The improved numbers make earlier estimates more confident, narrowing the range of possible surface conditions. When the radius and mass become more precise, scientists can better gauge how tightly the planet holds its air, how heat moves through its rock, and how pressure behaves from the surface down to deeper layers. The density estimate suggests that the planet is made mostly of rock and metal, much like Earth and other terrestrial bodies. A small part of its mass could come from lighter materials, but the overall picture shows a compact, solid world. This helps guide models of surface gravity and interior heat. A strong iron core can create a magnetic field if the interior cools at the right rate and if liquid layers move in complex ways. While no one can measure the magnetic field directly from this distance, scientists use comparisons with known rocky worlds to outline the conditions that might allow such a field to form. A magnetic field would help protect any atmosphere from charged particles over very long timescales. Temperature estimates are refined through careful analysis of how much radiation the planet absorbs. An orange star emits less ultraviolet light, so harsh surface effects would be weaker than on planets orbiting hotter stars. This difference matters for chemical reactions in the upper atmosphere. Too much ultraviolet energy can break down molecules faster than they form. Too little can slow chemical cycles needed to maintain long-term balance. If Kepler 442B sits within the moderate zone that supports these cycles at stable rates, it becomes easier for the planet to settle into long-lasting environmental patterns. Even without direct images, the idea of cloud systems comes from the way similar planets behave. Clouds form when water vapor or other gases cool as they rise, releasing heat and forming droplets or crystals. On a world with stronger gravity, clouds might sit lower because rising air would cool faster and reach the point of condensation at a lower altitude. If the atmosphere is dense, wide cloud layers could form and reflect large amounts of light. If the air is thin, clouds might be patchy and local. These ideas help scientists plan which wavelengths future telescopes should watch during transit events, since some wavelengths are more sensitive to cloud cover than others. The star's rotation period also plays a role. A star that rotates slowly tends to have calm magnetic activity and fewer dark spots. Kepler 442 shows this calmer behavior, which makes the transit data cleaner. When a planet passes in front of a star with many large star spots, the changes in brightness can be confused with atmospheric signals. A stable star reduces these problems, letting scientists extract more information from each pass. Clean data makes it easier to interpret faint signatures that might indicate atmospheric layers or scattering effects. Long-term brightness stability also helps in understanding orbital timing. A steady star allows scientists to record the exact moments when the planet crosses its face. By comparing many such transits, they can detect slight variations that may indicate additional planets or subtle gravitational influences. If the orbit remains steady across many years of observation, that steadiness supports the idea of a solitary planet with a predictable path. A stable orbit means consistent energy input over long spans of time, which is vital for climates that remain within moderate bounds. The study of how heat moves across the planet involves simple physics, but leads to rich insights. A rocky body with this mass will cool slowly, so heat from formation and radioactive decay continues to rise. That rise can shape surface activity. If deep layers remain warm, they may move in slow currents that shift crustal plates or maintain volcanic vents. These features can renew surface materials and release gases into the air. A planet without such activity tends to lose atmospheric molecules over time because there is no constant source replacing them. Even if no one can observe volcanic activity directly, the planet's mass and estimated composition make it reasonable to include such processes in climate models. The relationship between water and atmosphere is also part of these studies. Water vapor adds strong greenhouse effects, even in small amounts, so models explore whether modest levels of vapor could keep temperatures above the freezing point. The distance from the star suggests that the world receives enough energy for this balance to work if the air pressure is moderate. If the air is too thin, water would evaporate or freeze too easily. If it is too thick, temperatures might climb. Many possible combinations fall into a middle range that supports gentle cycles of evaporation, condensation, and precipitation. Refining the possible surface temperatures requires careful treatment of albedo, which describes how much light the planet reflects. A surface covered by bright clouds or ice would reflect more light, cooling the planet. A darker surface would absorb more energy, warming it. Scientists test a wide range of albedo values because they cannot see the surface directly. Yet the star's properties give a helpful boundary. Since the star is not bright enough to cause extreme heating, even darker surfaces would not push temperatures far outside the habitable zone. That reduces the uncertainty and suggests that many surface types could still fall within a mild range. By comparing this system to others around similar stars, patterns begin to emerge. Many orange dwarfs host planets within zones where moderate temperatures are possible. These stars burn their fuel slowly and stay stable for long periods. Their planets often receive steady amounts of light, making them prime targets for future atmospheric studies. Kepler 442B stands out because it sits at a distance that balances warmth and coolness in a way that places it near the center of the star's temperate zone rather than at the edge. This increases the chance that stable conditions have lasted for a long stretch of the star's life. Each new detail strengthens the foundation for understanding this distant world. The work remains slow because the planet is far away and faint, but the principles guiding each calculation are based on well-tested physics. Even without direct images, the information gathered so far outlines a world shaped by light from a calm star, by gravity strong enough to hold an atmosphere, and by interior heat that may support long-term geological cycles. As new tools come online, the picture will continue to sharpen, revealing more about how planets beyond our reach follow the same natural rules that guide the worlds we know. The investigation of Kepler 442B also considers the role of tidal forces between the planet and its star. While the planet is not extremely close, the gravitational pull from the star can still influence rotation over long periods. Tidal effects may slow the spin, potentially causing one side to face the star longer than the other. If this occurs, heat distribution becomes a crucial factor. A thick atmosphere could transport energy to the dark side, preventing freezing, while a thin atmosphere might leave extreme temperature differences. Modeling these effects provides insight into whether surface conditions remain mild or fluctuate sharply. Wind patterns, if they exist, are guided by rotation, gravity, and the uneven heating of the surface. On a larger planet, the Coriolis effect may differ from Earth's, changing how currents of air circulate. Atmospheric models show that heat moving from the illuminated side to the cooler regions could create steady, global winds that redistribute energy. These flows help maintain temperature balance, reducing harsh extremes and creating potential zones where liquid water can persist. Even without precise measurements, understanding these forces paints a clearer picture of the environment. The planet's potential for water also interacts with its internal heat. If the interior remains warm over billions of years, it can drive volcanic activity that releases gases and moisture into the atmosphere. This replenishes the air and maintains the water cycle. The presence of liquid water at the surface depends on a balance between energy received from the star and energy retained by the atmosphere. Too little heat and water freezes, too much and it evaporates rapidly. Kepler 442b's position and the star's energy output suggest that this balance could be maintained across a wide range of plausible atmospheric compositions. Solar radiation, while weaker than on Earth, still drives chemical reactions in the atmosphere. Molecules like water vapor, carbon dioxide, and methane respond to the light, creating cycles that can stabilize or modify the climate. Even moderate amounts of ultraviolet radiation initiate processes that convert some gases into others, shaping the chemical makeup of the air. These reactions are slow and continuous, providing a mechanism for self-regulation over geological timescales. The calm behavior of Kepler 442 means that extreme disruptions are unlikely, allowing these cycles to proceed steadily. Cloud formation is influenced by both gravity and available moisture. Stronger gravity may compress clouds closer to the surface, while warmer regions drive convection that lifts air and moisture. Clouds reflect some starlight, which cools the planet, and trap infrared radiation, which warms it. These opposing effects help maintain a temperature balance that is neither too hot nor too cold. While the specific height and density of clouds are unknown, the combination of gravity, atmospheric pressure, and energy input gives scientists boundaries within which clouds could form and persist. Seasonal variation depends on axial tilt, which cannot yet be measured. Even so, the star's steady output limits extreme seasonal shifts. If the planet tilts moderately, seasons could appear, but they would be less intense than on Earth because the star's light changes gradually across the year. If the tilt is minimal, the planet experiences consistent conditions year-round. Both possibilities support the idea of long-term environmental stability, a key factor in assessing the potential for habitability. Future observations may detect faint signs of atmospheric gases. Techniques like transmission spectroscopy examine how light passes through the planet's air during transit. Each molecule absorbs light at specific wavelengths, revealing its presence. Detecting water, carbon dioxide, or other simple molecules would refine understanding of climate, pressure, and potential surface conditions. While current technology struggles at this distance, incremental improvements continue to narrow the range of possibilities, allowing scientists to focus on the most likely scenarios. The planet's mass and radius together suggest a rocky composition capable of supporting internal heat. A solid core retains energy, producing convection that may drive surface activity over billions of years. This activity can release gases to replenish the atmosphere, maintain surface pressure, and support cycles of water and other compounds. Even without direct observation, physics provides a clear framework for these processes, and comparisons with Earth and similar-sized exoplanets reinforce the plausibility of such internal dynamics. The combination of gravity, energy balance, and rotation creates conditions favorable for moderate climates. Stronger gravity stabilizes the atmosphere. Star energy drives weather patterns, and rotation distributes heat. These elements interact naturally, producing a planet that could maintain liquid water in some form, even if it is patchy or seasonal. While the exact distribution remains unknown, the fundamental principles indicate that a stable environment is possible on a rocky world of this size, orbiting a calm K-type star. Observations also guide the understanding of reflectivity. Surface and cloud albedo influence how much energy the planet absorbs and releases. Higher albedo can prevent overheating, while lower albedo enhances warming. Variations in surface types, from dark rock to possible ice caps or cloud cover, alter the climate subtly. By simulating different albedo levels, scientists determine which combinations keep temperatures in a range where liquid water might exist, adding another layer of precision to climate models. By connecting these multiple factors, gravity, rotation, internal heat, star output, atmospheric composition, albedo, and orbital dynamics, researchers build a comprehensive picture. Each element interacts with the others, producing a network of influences that shape potential habitability. The planet cannot be observed directly in detail, yet the physics governing these interactions allow robust predictions about how energy, heat, and matter might behave on its surface and in its air. Kepler 442B becomes not just a distant signal, but a subject of careful, layered scientific understanding. Attention also turns to the ways Kepler 442b's atmosphere might circulate heat between equatorial and polar regions. On a world larger than Earth, air currents could extend across greater distances, moving warm air from regions facing the star toward cooler zones at higher latitudes. These flows reduce temperature extremes and maintain moderate climates. If water exists, these winds would interact with evaporation and condensation, producing clouds that shift slowly across the surface, spreading moisture and energy evenly. Even in the absence of oceans, differences in surface composition, rock, soil, possible ice, would influence the path of heat and wind, creating a complex but predictable system. The star's light also affects potential chemistry at the surface. Redder, lower energy photons penetrate differently than the full spectrum of sunlight on Earth. Chemical reactions that depend on ultraviolet light may proceed more slowly, altering cycles that create and destroy gases. Oxygen and nitrogen cycles, if they exist, would adapt to the available energy, producing stable atmospheres over long periods. Modeling these reactions shows that even with weaker ultraviolet radiation, a balance could develop, allowing gases to persist without rapid loss or accumulation. Surface features are influenced by both gravity and internal processes. The planet's stronger gravity means that any highlands or mountain ranges would rise less dramatically than on Earth. Valleys might stretch long and shallow, and any flowing water would carve broad channels rather than steep canyons. Volcanic activity driven by interior heat could release gases and reshape surface regions gradually, renewing soil and distributing minerals. This slow renewal contributes to a stable environment, providing the potential for long-lasting surface patterns that maintain moderate temperature ranges. The possibility of plate tectonics is also considered. If the crust is thick but flexible enough to move over time, the planet could recycle surface material. This process supports atmospheric stability, as gases trapped in rocks are released through volcanic activity. Plate tectonics also influences ocean distribution if water exists and shapes long-term geological structures. Even without observational confirmation, comparing the size, mass, and composition of Kepler 442 to known rocky planets provides reasonable support for the presence of slow, steady tectonic movement. The orbit itself contributes to stability. Slight eccentricity could create small seasonal changes, while a near-circular path would minimize temperature swings. Observations suggest the planet's orbit remains consistent across multiple transits, reinforcing models of predictable energy input. Predictable sunlight allows researchers to calculate potential average temperatures for a range of possible atmospheres, from thin to dense. These calculations form the backbone of habitability estimates, showing that the planet may remain within a temperate zone for billions of years. Magnetic protection is an additional factor. If the planet has a molten metallic core, rotation could generate a magnetic field that shields the surface from charged particles. The star's relative calm reduces the intensity of solar wind, allowing even a modest field to preserve atmospheric gases. This combination of gravitational retention, magnetic shielding, and steady stellar output creates a multi-layered defense against atmospheric loss, supporting the potential for long-term surface stability. Potential hydrological cycles are modeled using heat distribution, gravity, and atmospheric pressure. Water vapor, if present, rises in warmer regions and condenses in cooler areas, forming clouds and precipitation. Stronger gravity could compress these cycles closer to the surface, producing consistent but moderate patterns of rainfall or condensation. If liquid water exists in lakes or shallow seas, the interplay of evaporation, condensation, and gentle wind redistribution can maintain a balance that prevents extreme freezing or evaporation, sustaining a stable environment over geological timescales. Albedo variations continue to refine understanding. Dark surfaces absorb energy and warm more quickly, while reflective areas like ice or clouds reduce heating. Small changes in surface reflectivity shift local temperatures and atmospheric circulation. By modeling different combinations of surface types, scientists can explore scenarios in which the planet maintains moderate temperatures despite variations in landscape and cloud coverage. Each simulation adds confidence to predictions about which regions, if any, could sustain liquid water and stable atmospheric conditions. The star-planet system is studied as a whole, rather than focusing on individual aspects alone. Gravity, orbit, stellar output, rotation, atmosphere, internal heat, clouds, and surface reflectivity interact in ways that create predictable patterns. Each factor supports or modifies the others, producing a system in which conditions remain relatively stable. This integrated approach allows scientists to estimate how the planet behaves over millions or billions of years, highlighting the unique balance of traits that makes Kepler 442b one of the most carefully analyzed candidates for potential habitability. Finally, comparisons with similar exoplanets help validate models. Researchers examine how planets of similar size and orbit respond to K-type stars. The consistency of outcomes strengthens confidence in the projections for Kepler 442b. While direct observation remains impossible, these comparative studies provide an indirect form of evidence, suggesting that the planet's combination of mass, orbit, stellar energy, and internal dynamics likely results in a surface and atmosphere capable of maintaining moderate, stable conditions. Attention then turns to the long-term evolution of Kepler 442b's atmosphere. Over billions of years, gases escape slowly into space, but strong gravity and a relatively calm star reduce this loss. Light molecules like hydrogen and helium may drift away, while heavier gases such as nitrogen and carbon dioxide remain. These heavier molecules create pressure that supports liquid water, if it exists, and sustains moderate temperatures. The balance between escape and replenishment, potentially aided by volcanic outgassing, shapes a stable, enduring environment that can persist across vast spans of time. The planet's interior also influences surface conditions indirectly. Heat rising from the core drives convection within the mantle, slowly reshaping the crust and affecting volcanic activity. This release of internal energy allows chemical cycles to continue, feeding gases into the atmosphere and contributing to surface renewal. Rocks exposed by such activity may interact with water and atmospheric gases, gradually modifying the composition of the environment. Even without oceans, small reservoirs of liquid or frozen water could participate in chemical exchanges that help stabilize the climate. Energy distribution across the planet is a subtle but essential factor. Incoming starlight is absorbed differently by land, water, and clouds. Surface temperature patterns emerge as energy spreads from warmer regions to cooler ones through atmospheric circulation and possible ocean currents. If clouds form, they both trap heat and reflect sunlight, smoothing temperature differences. These processes combine to create a planet where extremes are reduced, making large portions of the surface more likely to remain within a moderate temperature range suitable for liquid water. Seasonal and diurnal cycles contribute additional nuance. Rotation may create regular day and night periods, giving the atmosphere time to circulate energy evenly. Axial tilt, even if modest, introduces slow seasonal changes that can affect cloud formation, precipitation, and local temperatures. These slow, rhythmic variations provide a dynamic yet stable system, preventing stagnant conditions and ensuring that energy is redistributed continually. Even without precise measurements, models can predict the general range of variation and confirm that it would not produce uninhabitable extremes. The composition of potential clouds is also considered. Water is the most common candidate, but other molecules like carbon dioxide or sulfur compounds could form clouds if present in sufficient quantities. Cloud height, density, and coverage influence how much sunlight reaches the surface and how heat is retained. On a planet with stronger gravity, clouds may sit lower and circulate more slowly, producing soft, widespread layers rather than rapid, towering formations. This could create gentle weather patterns, reducing the likelihood of destructive storms and contributing to an overall calm climate. Chemical stability in the atmosphere is closely linked to stellar radiation. The red-orange light from a K-type star interacts differently with gases than sunlight on Earth. Reactions that depend on higher energy ultraviolet light occur more slowly, creating a more gradual turnover of molecules. This slow pace can support equilibrium conditions over long timescales, keeping the atmosphere from being stripped or chemically imbalanced. The result is an environment that changes gradually, providing consistency essential for any long-term surface processes. Volcanic and tectonic activity may be less dramatic than on smaller, more geologically active planets, but the effects are steady and cumulative. Over millions of years, lava flows, volcanic gases, and shifting plates renew surface materials, redistribute minerals, and help maintain atmospheric balance. Even small volcanic vents could release water vapor, carbon dioxide, or other gases, contributing to the chemical cycles that moderate climate. This slow renewal contrasts with catastrophic events, emphasizing the quiet, persistent processes that shape the world over time. Observations of the star's output inform predictions about surface conditions. The star's steady luminosity allows models to calculate average energy absorption with reasonable confidence. Small fluctuations in brightness produce only minor variations in surface temperature, preventing extreme climate swings. This consistency, combined with a moderate planetary orbit, supports the idea that any liquid reservoirs remain stable. Researchers can simulate multiple atmospheric compositions under these energy conditions identifying which scenarios produce gentle, sustained climates. The potential presence of water influences both climate and geology. Evaporation from small seas or lakes can drive local winds, distribute moisture, and contribute to cloud formation. Precipitation returns water to the surface, supporting cycles that maintain humidity and temperature balance. Even in partial or intermittent water systems, these feedback loops help moderate extremes, creating zones where surface conditions remain within ranges suitable for stable chemical interactions. The result is a self-regulating system that gradually adjusts to incoming energy and internal processes. By integrating these factors, gravity, stellar output, orbital stability, rotation, axial tilt, atmospheric composition, clouds, volcanic activity, and potential water, scientists construct a coherent picture of Kepler 442B as a planet capable of maintaining long-term, moderate conditions. Each layer of analysis builds upon the others, reinforcing the conclusion that the planet's characteristics interact to produce a world where energy, matter, and heat flow in a steady, balanced manner. Even without direct imaging, the synthesis of observation and theory reveals a distant planet shaped by consistent natural forces, quietly evolving over billions of years. Attention turns next to the delicate interplay between the planet's atmosphere and the energy received from its star. On Kepler 442b, sunlight arrives with a slightly redder hue than on Earth, subtly changing how heat is absorbed and dispersed. Surface materials react differently. Darker regions capture more energy, while lighter areas and clouds reflect it back into space. This dynamic creates patterns of warming and cooling that shape air currents, influencing where moisture rises and condenses. Over long periods, these processes form a self-consistent climate, distributing energy in a manner that prevents extremes and allows surface regions to remain temperate. The depth and pressure of the atmosphere play a critical role in moderating temperatures. A thicker atmosphere retains heat more effectively, evening out differences between day and night sides. Even if one region receives more sunlight than another, winds and thermal circulation transport energy across the surface, reducing local extremes. Conversely, a thinner atmosphere allows faster temperature swings, but Kepler 442b's gravity favors the retention of gases, making a moderate, stable atmosphere more likely. Scientists use models to explore the range of pressures that produce persistent liquid water without generating severe heat or cold. The potential for volcanic outgassing is linked directly to climate stability. Heat from the planet's interior drives slow movement within the mantle, producing vents that release gases such as carbon dioxide, water vapor, and nitrogen. These gases replenish the atmosphere, replacing molecules lost to space and maintaining pressure. Over millions of years, this quiet process shapes a stable environment. Even minor contributions accumulate, sustaining cycles that regulate temperature and humidity and supporting the long-term persistence of a temperate surface. Tidal interactions continue to influence rotation subtly. While the planet is not close enough for extreme tidal locking, the star's gravity may gradually affect the length of a day. If rotation slows slightly, temperature differences between illuminated and darker regions would increase, but circulation within the atmosphere could compensate. This interaction ensures that surface conditions remain moderate, preventing dramatic extremes in either heat or cold, and allowing weather patterns to function predictably. Water, if present, shapes both surface and atmosphere in multiple ways. Evaporation from liquid reservoirs generates moisture that rises and condenses in cooler regions, forming clouds. Precipitation then returns water to the surface, completing a cycle that regulates temperature and distributes energy. Even partial or seasonal bodies of water can drive local wind patterns, which in turn support cloud formation and energy redistribution. This interconnected system illustrates how relatively simple physical processes combine to produce a dynamic, balanced environment. Cloud formation itself depends on gravity, temperature gradients, and available moisture. On a planet slightly larger than Earth, clouds may form lower in the atmosphere due to stronger gravity compressing air layers. These clouds can blanket extensive areas, reflecting incoming light while retaining outgoing infrared radiation. The result is a moderating influence, softening temperature extremes and maintaining surface regions within a range suitable for liquid water. Simulations show that even moderate cloud cover can significantly enhance climate stability, reinforcing the likelihood of long-term temperate conditions. The chemical composition of the atmosphere interacts with stellar radiation in subtle ways. Red-orange starlight penetrates the atmosphere differently than sunlight on Earth, influencing reactions that govern the abundance of gases like carbon dioxide, water vapor, and methane. Chemical cycles proceed at a slower, steady pace, allowing the atmosphere to maintain equilibrium over millions or billions of years. This slow turnover supports the persistence of surface conditions without sudden disruption, contributing to a sense of quiet, continuous stability. Internal geological activity contributes additional layers of stability. Slowly moving tectonic plates and intermittent volcanic eruptions recycle surface material, release gases, and modify terrain gently over time. These processes distribute minerals, maintain atmospheric composition, and prevent stagnation in surface chemistry. While these changes are imperceptible over human timescales, they provide the foundation for an environment that can sustain moderate conditions indefinitely. The combination of internal heat, gravity, and rotation ensures that these geological processes continue quietly and steadily. Observations of the star-planet system as a whole reinforce the view of a stable world. Kepler 442's steady light output, moderate activity, and long lifespan create predictable energy input. Coupled with the planet's mass, gravity, potential atmosphere, and internal heat, the system forms a network of interacting forces that favor long-term equilibrium. Each factor complements the others, producing an environment where temperatures, pressure, and chemical composition remain relatively constant. In this distant system, the laws of physics and the quiet work of time combine to create a planet shaped by balance and continuity, a world that may quietly host conditions suitable for life as we understand it. As the study of Kepler 442b deepens, researchers consider the long-term interplay of energy, atmosphere, and surface. Heat from the star interacts with clouds, land, and any water bodies, driving currents that carry warmth across the planet. Cooler regions receive energy indirectly through winds and circulating air, preventing harsh temperature extremes. Over millions of years, this steady transfer of heat shapes patterns of evaporation, condensation, and precipitation that may repeat rhythmically, maintaining moderate climates without sudden shifts. The influence of gravity extends beyond shaping terrain and clouds. Stronger gravity retains atmospheric gases, supporting pressure levels that favor liquid water. It also moderates wind speed, preventing violent storms from forming easily. On larger land masses, air currents flow in broad, gentle paths, distributing energy evenly and interacting with surface features to stabilize temperature and humidity. These dynamics suggest a slow, deliberate movement of air and moisture, rather than abrupt, unpredictable changes. Volcanic activity, while subtle, contributes to chemical balance in the atmosphere. The release of carbon dioxide, water vapor, and nitrogen replenishes molecules lost to space or chemical reactions. Over time, this ongoing renewal helps maintain a consistent surface pressure. Lava flows reshape the crust slowly, creating new rock surfaces that interact with water and atmosphere, forming feedback loops that regulate climate. Even small volcanic events accumulate over eons, reinforcing the quiet stability of the environment. The potential for oceans or large lakes enhances this system. Water absorbs and stores energy, moderating local temperatures and providing a medium for evaporation and precipitation. Liquid water interacts with the atmosphere to sustain moisture cycles that move heat from warmer to cooler regions. The balance of evaporation and rainfall, combined with gentle winds, allows water to remain liquid in many regions for extended periods. Even if water is unevenly distributed, these cycles contribute to regional stability. Axial tilt, if present, creates slow seasonal changes. Mild shifts in sunlight across the planet induce variations in temperature and cloud formation. These seasonal rhythms provide a natural pacing to energy distribution, allowing the atmosphere and potential water cycles to adjust gradually. Even modest tilt reinforces the consistency of environmental conditions, promoting a stable climate without sudden disruptions. The star's long-term stability underpins all of these processes. Kepler 442 emits light steadily over billions of years, minimizing the risk of abrupt climate changes caused by stellar flares or luminosity swings. This consistency ensures that energy input remains predictable, allowing atmospheric, oceanic, and geological systems to develop and persist without extreme stress. Each element interacts gently with the others, producing a self-regulating planetary system. Cloud formation continues to moderate temperatures, reflecting light during the day and trapping heat at night. On a planet with strong gravity, clouds may form lower and more evenly, distributing moisture slowly across wide areas. This reduces the likelihood of localized overheating or cooling and supports the steady operation of weather cycles. The clouds themselves participate in energy transport, moving heat both horizontally and vertically, maintaining equilibrium between surface and atmosphere. Internal heat from the planet's core interacts with surface processes. Convection in the mantle drives subtle shifts in crustal plates, creating volcanic vents that release gases. These processes replenish atmospheric components, contribute to surface renewal, and maintain chemical cycles necessary for long-term stability. Over millions of years, the combined effect of interior heat, volcanic activity, and surface interactions reinforces a climate that remains moderate and persistent. The distribution of surface reflectivity, or albedo, also affects the planet's climate. Bright areas, such as clouds or potential ice caps, reflect sunlight and prevent overheating, while darker regions absorb energy, moderating cooling. These variations create gentle gradients that support the movement of air and moisture. By simulating multiple albedo scenarios, scientists can predict which surface compositions lead to stable, temperate conditions that favor the long-term persistence of liquid water. The synthesis of all these factors presents a coherent view of Kepler 442b. Gravity, stellar energy, atmospheric composition, rotation, axial tilt, cloud cover, water cycles, internal heat, and surface reflectivity interact to produce a world governed by balance. Each process supports and moderates the others, creating an environment that changes slowly and predictably over geological time. The planet, though distant and unseen in detail, emerges as a subject of careful scientific understanding, shaped by quiet, consistent forces that preserve stability and the potential for habitable conditions. Scientists also consider the subtle effects of atmospheric circulation on heat distribution. As air moves from warmer to cooler regions, it carries energy that smooths temperature differences across the planet. On Kepler 442b, strong gravity and moderate rotation likely produce wide, gentle currents that transport warmth evenly. This circulation interacts with clouds and surface features, creating a system where heat spreads gradually rather than concentrating in any single area. The result is a surface climate that changes slowly, supporting persistent temperate conditions over long stretches of time. The composition of the atmosphere shapes these patterns further. Nitrogen, carbon dioxide, and water vapor dominate the expected mixture, each contributing differently to heat retention and chemical balance. Carbon dioxide absorbs infrared energy, keeping the surface warm at night, while water vapor participates in evaporation and condensation cycles that drive clouds and precipitation. Nitrogen provides bulk pressure, helping retain water in liquid form. Together, these gases create a framework for stable temperatures and ongoing chemical cycles, sustaining the environment in a predictable rhythm. Volcanic contributions, though subtle, provide ongoing adjustments to atmospheric balance. Molten rock releases gases slowly over millions of years, maintaining pressure and replenishing molecules lost to space. Lava flows reshape land masses incrementally, creating new surfaces that interact with air and water. Even small amounts of gas released consistently over geological timescales can stabilize temperature and pressure, contributing to the gentle, enduring patterns that define the planet's climate. The distribution of energy across the planet's surface is influenced by both latitude and topography. Regions closer to the star's direct rays receive more energy, warming faster, while higher latitudes receive less, remaining cooler. Mountain ranges and valleys channel air currents, guiding winds that carry heat and moisture. This complex interplay of sunlight, surface features, and air movement ensures that temperature variations remain gradual, preventing sudden extremes. Even small shifts in topography affect local climates, adding texture to the planet's overall energy balance. Water, when present, amplifies this moderating effect. Oceans, lakes, or even scattered liquid reservoirs absorb heat during the day and release it at night, softening temperature swings. Evaporation adds moisture to the air, supporting cloud formation and precipitation that further redistribute energy. These processes operate in a cycle, balancing heating and cooling across regions and maintaining conditions suitable for liquid water. Even if water is patchy, its influence spreads beyond its immediate location, shaping regional climate patterns. The slow rotation of the planet contributes to the steadiness of day-night cycles. If the planet rotates at a moderate pace, temperatures rise and fall gradually, giving the atmosphere time to circulate energy evenly. Longer days allow sunlight to warm surfaces gently, while nights cool slowly, preventing rapid drops in temperature. This rhythm, coupled with cloud and wind patterns, produces a steady pace of environmental change, reinforcing long-term stability. Axial tilt, although unknown, would introduce gentle seasonal variations. A slight tilt shifts sunlight gradually over the course of the orbit, influencing cloud distribution, surface temperatures, and precipitation patterns. These slow changes provide a dynamic element to the climate, allowing energy and moisture to redistribute across the planet without causing extreme weather. The combination of rotation, tilt, and atmospheric circulation creates a planet where climate evolves gently over time. Albedo continues to influence the balance of heating. Light-colored clouds and potential ice reflect sunlight, cooling the surface, while darker areas absorb energy, mitigating nighttime cooling. This interplay of reflective and absorptive surfaces creates gradients that guide air and moisture movements. Small adjustments in surface reflectivity can shift local conditions slightly, but the overall system remains stable, allowing for persistent temperate zones that could support liquid water. The planet's magnetic field, if present, shields the atmosphere from charged particles emitted by the star. This protection reduces atmospheric loss and preserves chemical cycles essential for maintaining pressure and temperature balance. The star's calm behavior means that even a modest field is sufficient to sustain long-term stability. Together, these factors, circulation, chemistry, volcanic replenishment, energy distribution, rotation, axial tilt, albedo, and magnetic protection, form a cohesive, interdependent system that keeps the planet's environment moderate and enduring over immense timescales. Attention turns to the subtle interplay between surface features and atmospheric behavior. Mountains, valleys, and plains guide the flow of air, shaping wind patterns and influencing where clouds form. Higher elevations may cool more quickly, causing moisture to condense and create localized precipitation. Plains and lowlands allow air to move freely, spreading warmth and humidity across broad areas. This constant interaction ensures that energy from the star is redistributed steadily, producing a climate that changes gradually rather than abruptly. The retention of heat by the atmosphere also interacts with the potential presence of water. Moist air rises, cools, and condenses into clouds, which reflect incoming starlight while trapping infrared energy emitted from the surface. Rainfall or condensation returns moisture to lakes, rivers, or soil, completing a gentle cycle that moderates temperature and maintains environmental equilibrium. Even in regions where water is scarce, these cycles help distribute heat and humidity, sustaining moderate conditions across the planet. Geological activity beneath the surface contributes quietly to atmospheric balance. Mantle convection drives slow shifts in the crust, producing minor volcanic eruptions that release gases into the air. Over time, these gases replenish components lost to chemical reactions or space, stabilizing pressure and temperature. Lava flows alter surface texture gradually, influencing how heat is absorbed and radiated, and providing fresh material for chemical interactions. This continuous process reinforces the self-regulating nature of the planet's environment. Wind currents respond to both rotation and differential heating. Areas receiving more sunlight warm the air, causing it to rise and flow toward cooler regions. The cooler air descends, creating circulation patterns that transport energy across the planet. Strong gravity helps contain these currents, preventing extreme turbulence and maintaining smooth movement. These consistent winds aid in distributing heat evenly, preventing large temperature contrasts and promoting a climate suitable for liquid water. The star's light also interacts with atmospheric molecules, driving chemical reactions that proceed slowly under lower energy red-orange radiation. Water vapor, carbon dioxide, and nitrogen undergo transformations that influence cloud formation, greenhouse effects, and overall pressure. Because these reactions progress gradually, the atmosphere remains chemically balanced over long timescales, supporting steady temperatures and stable surface conditions. Surface reflectivity influences energy absorption. Brighter regions, including clouds or ice, return more light to space, preventing overheating, while darker surfaces absorb heat, moderating nighttime cooling. Variations in reflectivity create gradual gradients of temperature that guide winds and moisture flow. These subtle differences contribute to the overall balance of the climate, helping maintain a range of conditions favorable to liquid water without abrupt shifts. Orbital dynamics continue to shape the planet's environment. A nearly circular orbit ensures a consistent amount of energy reaches the surface, limiting extremes caused by fluctuating distance from the star. Slight eccentricity could induce gentle seasonal shifts, but the overall stability allows climate patterns to develop predictably. The combination of steady energy input, planetary rotation, and axial tilt supports the formation of rhythmic, long-term cycles of temperature, cloud formation, and precipitation. Water, even in limited quantities, enhances climate stability. Evaporation from lakes, rivers, or shallow seas generates moisture that circulates through the atmosphere, forming clouds and producing rainfall or condensation. This circulation distributes heat and water evenly, reducing temperature extremes and supporting moderate surface conditions. The interplay between liquid reservoirs, atmospheric movement, and energy from the star establishes a continuous, self-regulating system that persists over geological timescales. Gradual changes in cloud density and distribution influence temperature regulation. Thick cloud cover reflects sunlight during periods of strong illumination while retaining warmth at night. Localized variations create gentle fluctuations, but the overall effect smooths energy distribution across the planet. Even partial cloud coverage contributes to moderating conditions, reinforcing the balance established by atmospheric composition, circulation, and surface features. The interaction of these factors, air movement, chemical cycles, surface features, water, cloud formation, energy absorption, and orbital dynamics, creates a coherent system in which climate remains stable. Each element supports the others, producing a world where temperature, pressure, and chemical composition evolve slowly and predictably. Kepler 442B, observed from across the cosmos, emerges as a planet shaped by consistent natural processes, quietly maintaining conditions that may allow liquid water to exist for billions of years. The continuous influence of internal heat shapes the planet subtly yet persistently. Warmth, rising from the core, drives convection in the mantle, slowly shifting rock and influencing volcanic activity. Even minor eruptions release gases that replenish the atmosphere and contribute to pressure stabilization. Over millions of years, these processes help maintain chemical cycles and moderate climate, producing a surface environment that changes gradually rather than abruptly. Each volcanic contribution, while individually small, accumulates over geological timescales to sustain long-term stability. Surface water, if present, acts as a thermal buffer. Lakes, shallow seas, and rivers absorb heat during periods of illumination and release it gradually at night. This moderates temperature swings, keeping surface regions within a range where liquid water can persist. Evaporation from these bodies feeds atmospheric moisture, supporting cloud formation and gentle rainfall. The combined effect of energy absorption, moisture cycling, and wind circulation produces a climate in which extremes are limited and temperate conditions can persist across vast regions. Wind patterns continue to play a critical role. Warm air rising from heated surfaces moves toward cooler areas, while cooler air descends to replace it, generating consistent circulation. Gravity confines these flows, preventing turbulent, unpredictable patterns. Over long periods, this slow, continuous movement of air distributes energy evenly, reducing temperature differences between illuminated and shaded regions. The result is a surface climate that evolves gently, supporting the maintenance of liquid water where it exists. Cloud formation responds directly to atmospheric circulation and surface moisture. Rising warm air carries water vapor that condenses at higher altitudes, forming clouds that reflect sunlight and trap infrared radiation. This dual effect stabilizes temperatures both day and night. Clouds shift gradually with prevailing winds, creating dynamic yet balanced coverage that enhances climate moderation. Even partial cloud layers contribute to consistent surface conditions, regulating energy distribution and reinforcing the planet's environmental equilibrium. The red-orange light from the star continues to shape chemical cycles. Lower energy radiation interacts with atmospheric gases, driving slow reactions that influence greenhouse effects and cloud formation. Water vapor, carbon dioxide, and nitrogen molecules participate in these transformations, which proceed steadily over time. The slow pace ensures chemical stability, preventing rapid imbalances that could disrupt climate. In combination with volcanic replenishment, orbital stability, and surface reflectivity, these reactions contribute to a resilient planetary environment. Axial tilt and rotation synchronize with atmospheric processes to smooth day-night and seasonal variations. Moderate rotation allows gradual heating and cooling, giving the atmosphere time to circulate energy evenly. A small tilt produces mild seasonal shifts, moving sunlight gradually across the planet's surface. These rhythms enhance stability, allowing moisture, temperature, and cloud systems to adjust slowly rather than abruptly. The interplay of rotation, tilt, and circulation ensures a predictable, balanced climate. The combined effects of gravity, atmosphere, water, wind, clouds, internal heat, chemical cycles, albedo, orbital stability, rotation, and axial tilt form an integrated system. Each factor supports the others, producing a planet where energy and matter move in a controlled, continuous fashion. The interactions are subtle, cumulative, and long-lasting, creating conditions in which liquid water can persist, chemical cycles remain stable, and temperatures stay moderate across extensive regions. Kepler 442B presents itself not as a place of dramatic events, but as a world defined by quiet balance, gently evolving under the predictable laws of physics. As observations continue, the potential for habitability remains a central focus. By combining models of atmospheric composition, surface features, hydrological cycles, and stellar influence, scientists refine predictions about where moderate temperatures and liquid water might exist. Each simulation reinforces the view of Kepler 442B as a stable, enduring environment. The planet's characteristics, mass, gravity, energy input, rotation, and chemical cycles interact in a way that produces equilibrium, offering a calm, steady surface across which energy and matter flow naturally over billions of years. Reflecting on the system as a whole, it becomes clear that Kepler 442 embodies a delicate harmony. Every element, from internal heat to clouds, from water cycles to orbital precision, contributes to a slow, consistent rhythm. The star provides a steady light. The planet's gravity holds gases and water, and chemical processes proceed gently. All these factors combine to produce a world in which conditions change subtly and predictably. A planet quietly shaped by natural forces, maintaining the potential for liquid water and habitability over immense spans of time.